Hi friends, this is probability and stochastic process, homework 11, question 1. I'm Smith. In the first question, we are given that x of t is a stochastic, real, wide sense stationary process, and its autocorrelation function is r of tau, and its spectral density is s of omega. Now we have to show that the autocorrelation function is real and even. So let's try to show the first property. Now x of t is real, so therefore it does not contain any imaginary part. So therefore x of t has a real plus no imaginary part. The imaginary part is 0 in this case. So if we take its conjugate, it's also a real value because the conjugate does not matter as there is no imaginary part in it. Also, x of t plus tau, t plus or minus tau is real, and similarly x conjugate of t plus or minus tau is also a real value. So from this we can say that the autocorrelation function has to be a real value because autocorrelation is defined by r of tau, which is the expected value at two different time instants, that is t plus tau into x conjugate of t. So here x conjugate of t will be equal to x of t as x contains only the real part. So this is clear that the autocorrelation function is also a real value. So this will be some real value. Now let's try to show that it's also an even function. So for that we have, by definition, by definition of autocorrelation, we have r of tau equals to expected value of x at t plus tau, and let's say at time instance t and t plus tau. So we know the definition of here x is a wide sense stationary. So wide sense stationary means that its mean value will not change over its entire time period. So the expected value or the mean value is not going to change. So we can rewrite this as, now let's just shift it by time instant tau. So we are just making a shift here. And we can see that we have just shifted this autocorrelation function of x by tau, and its expected value would not change because x of t is WSS and it's given. So for wide sense stationary, the mean value would be same. So now let's try to see what is r of minus tau. So autocorrelation function for minus tau is the expected value at time instance x of t minus tau and x of t. So this is nothing but this. So if we see that the tau is going to cancel, so this is x of t, and this again is x of t minus tau, which is similar to this x or r of minus tau. So we can say that r of tau is equals to r of minus tau, and therefore autocorrelation is an even function. Now let's try to solve the second part, which is we have to show that the spectral density is also even and non-negative. The spectral density is even and non-negative. So let's start with the definition of spectral density. So the definition is S of omega. In other words, we can say that the spectral density is the Fourier transform of the autocorrelation function. So the Fourier transform of autocorrelation function, that is r of tau into e over minus omega tau d of tau. So now let's try to see what the s of minus omega is. So s of minus omega would be equal to s of integral over minus infinity to infinity r of tau e over here instead of tau we have minus tau, so it would be instead of omega we have minus omega, so this will be positive e over j omega tau d tau. Now let us take another variable lambda such that tau is equals to minus lambda, so therefore this would be d tau is equals to minus d lambda. Now s of minus omega is equals to limits are going to change. It would be from plus infinity to minus infinity r of minus lambda e over minus omega lambda minus d lambda. So let's take this minus sign in front, and this minus sign we can change the limits, so it would be from minus infinity to infinity r of minus lambda e over minus j lambda d lambda. Now we know that the autocorrelation function is an even function, so r of minus lambda would be same as r of lambda. Now this is even, this is even. We know that from the previous from the previous part of the question. So, and this is nothing but what we started with. So that was the definition of the spectral density. So S of minus omega is equals to S of omega. So we can conclude that the spectral density is also an even function. The spectral density is also an even function given that the function x is itself real and Whiteson stationary. Now let's try to show the second part, that is it is a non-negative as well. So for non-negative we have for S of omega to be non-negative, let's try to see what its conjugate looks like. So S conjugate of omega equals to integral from minus infinity to infinity conjugate of autocorrelation into j omega tau d tau. Now we know that there is a property, skew symmetric property of the spectra of the autocorrelation, which says that the conjugate is equal to the r of minus tau. So therefore, using the property of skew symmetric property of autocorrelation, we have r conjugate equals to r of minus tau. So we can write this function as r of minus tau e over j tau d tau. Now again, let's suppose that tau is equals to minus lambda. Let tau is equals to minus lambda. So its integral is again going to change from infinity to minus infinity, this negative sign in the front because of d lambda, and we'll have r of lambda e over minus omega lambda d lambda, and this is, we know that this is the definition itself, minus infinity to infinity r of lambda e over j omega lambda d lambda, and this is nothing but S of omega. So S conjugate of omega is equal to the positive spectral density S of omega. So therefore S of omega is also non-negative. So this was question 1 of homework 11. Thank you.